All right, let's start. Good morning, good afternoon, everyone. Thank you for joining our Expert Exchange series, and welcome to our Expert Exchange on the flexibilization and repurposing of coal-fired power plants. Before we start, my name is Martin Keim. I'm a policy advisor at the IKI JET project, Just Energy Transitions in Coal Regions, and I have the pleasure to moderate today. So I will give you a couple of elements for to guide us through today's presentation, a couple of housekeeping rules before we dive right into our discussion. For today's expert exchange, as for any other expert exchange, you will have translation options. So there are two main different options. You can dial into the expert exchange via the browser, via your web browser. To do that, you have to click on the following link that you'll find in the presentation now on your screen, or you can also scan the QR code that is now visible on the left-hand side. You then click on the languages that on the language that you would like to select, and then you just press the play button. There is to basically do that, you have to mute your Teams sound. So that means, again, two different options. If you're joining our Expert Exchange via the Teams app, you can select that on the audio settings. You just click on the three dots on the top right of the screen. You click on audio settings, and then you select the loudspeaker icon to mute. That's important, so otherwise you will hear a double sound. So it's important to mute that. If you select a translation option, then you can just go via the translation audio. And the other option via Teams is to select through the browser. So if you're joining through the browser today, you can just select again on the mute side or mute tab option at the browser tab. And then a second option to joining the translation is via the Interactio app. You can download the app via scanning this QR code on the left. You enter the meeting code. It's IKI JET 2025. You select your preferred language, and then you just you press play to hear the meeting in your selected language. Great. So now, with that being said, again, warm welcome to everyone joining us today. We're very happy to have you joining this very vibrant discussion on a timely topic of flexibilization and retrofitting of coal-fired power plants. We have with us today a distinguished panel that I will introduce to you in a bit. And just to also introduce a little bit the idea of today's event to the flow of this event. We wanted to tackle the flexibilization and repurposing topic of coal-fired power plant because of various angles that we encountered in our work. A lot of discussions came from the question of how can you use coal assets that are changing their function in an energy system that is increasingly dominated by renewables. How can flexibilized coal-fired power plants enable higher renewable integration? But at the same time, the risks linked to that. So how is it, for instance, maybe also a possible risk to avoid if coal-fired power plants are a problem to mitigate emissions in the short term, if that is a problem, that we will discuss that as well. What are the costs also for flexibilization options? So all these questions arose in various of our countries that we will dive into a bit deeper in a minute. But it's just to set you the context for today, and we will look at these different questions from a perspective at different levels. So we will start with the energy systems level, the power systems level. And then we will look at the operational level at the power plants themselves, more generally speaking, what kind of interventions, what technical parameters, and then we will look at country examples, of course, which countries have made what experience with regards to flexibilization. So that's the plan for today. And now I will say a few words on our guests and on our project, and then we can dive right in. So if you we have today with us from the German Aerospace Center, Dr. Jürgen Kern and Andreas Meurer. We have Dr. Claudia Weiser from VGBE. VGBE Energy is the German Power Plant Association. Then we have Jorge Moreno and Victoria Fröhlich from Inodú, a Chilean energy consultancy and engineering consultancy company. So if you go to the next slide, please. A quick introduction on IKI JET, the Innovation Regions for a Just Energy Transition project. For those of you who haven't heard of IKI JET before, we are funded by the German government and the European Commission. So we are basically a global platform of core regions that that comprises countries such as Chile, Mongolia, South Africa, Thailand, Vietnam, and then we have Indonesia and Colombia included as well, with both having two separate country components. The IKI JET project is not only implemented by GIZ, we are a consortium of organizations, as you can see in the slide here. We work together with CAN International, the International Institute for Sustainable Development, the International Labour Organization, Solidarity Center, the Union Abroad, AFIDA, and the Wuppertal Institute. And our project is, as you can see, currently basically in the middle of the final implementation, the third of the project, I would say. As you can see, we started in December 22, and our project duration is still going to be until January 2027. Yeah, thanks for the next slide. And in a nutshell, one slide back. Thanks. Just to quickly, in a nutshell, the project has three different components. We are on the first project component is the JET-CR platform, as you've just now been introduced to, and of which this expert exchange today is part of. That comprises the 7 countries I just mentioned. We have including in this component also a policy dialogue and our knowledge hub, where you will find all the information on different publications, studies, interesting insights, events on just energy transition and coal phase out online. It's our one-stop shop basically, and you can access it via the chat and the links that have been shared in the chat now. Then we have 2 country components, one in Indonesia and one in Colombia, with a specific topical focus. Okay, so much for the quick introduction to IKI JET. Now let's dive right in. As I mentioned, we will start with the topic at a system level, so at the power system level, to be more precise. And we will start with an input from Dr. Jürgen Kern and Andreas Meurer. Jürgen Kern is a research associate at the German Aerospace Center, DLR, and he works in the Department of System Analysis and Technology Assessment. Andreas Meurer is also a research associate and a PhD candidate at the German Aerospace, specializing on energy systems analysis, synthetic fuel production, and we have the pleasure to work with both in a study that we're currently conducting. So without further ado, I would like to hand over now to Jürgen and Andreas, who will look at today's topic from a energy systems level perspective. Thank you very much.
Thank you very much, Martin. It's a pleasure and honor to present our competences and our contribution to this very important project. on the level of system analysis. So DLR, one of Germany's largest research centers, with about 11,000 people, mainly focused on aviation and aerospace. We also have a system analysis team, which is actually about 100 people in the Institute of Energy Systems. And we are focusing on general analysis of energy systems. That means typically country systems, regional systems. We look at the overall composition, and my microphone is deactivated. No. Can you still hear me?
We can hear you. Jürgen.
Okay.
No problem.
We're looking at the overall energy system of a country, especially about the system of today and their options into the future. The future means the years 2030, 40, 50, and we're developing scenarios. This is what-if analysis. So we don't make any predictions. This is a couple of scenarios about the future, because it's impossible to predict the future, but we can prepare for the future. And this is what we do with very sophisticated tools. And we use these tools for the analysis of the flexibility and repurposing of coal-fired power plants in 4 countries within the IKI JET project. And Andreas, my colleague, who is the expert in modeling and simulating these energy systems, will now go into a little bit more details. Andreas, please.
Yeah, thank you, Jürgen, for the introduction, and also thank you, Martin, for the nice introduction. Yeah, next slide, please. So the target, let's say, of the next 10 to 15 minutes is that you will learn a bit more about our study itself. So this is an ongoing study. It's not finished yet, so we will not present any results, but we will show you our approach, the approach we are taking to get a better understanding. And the second target is to highlight why we think that the systematic approach is a relevant component in the entire universe of assessing CFPP flexibilization options, and why we think that a systemic approach and systemic assessment is definitely important to get a better understanding about the feasibility of different options we have on the table. So first, our study has some guiding questions. So we know there are different technical options for existing CFPP sites for a future flexibilization or repurposing of existing components that are part of an energy system. And we know that they have to operate as part of a future energy system. And the future energy system always will look different than today's energy system, because there's always development, usually now on a global scale, towards more sustainable energy systems. That means usually an increase in renewable energy penetration, but we also have to deal with also usually an increase in electricity demand over time. And we want to understand how those different flexibility or repurposing options would behave in a future energy system. And a typical way of doing energy systems analysis is to develop scenarios. So how could the future look like? And usually you do a set of, let's say, 3 to 5 different scenarios that might be realistic and might cover different realistic pathways where an energy system might develop. But we want to broaden the scope a bit. As Jürgen just said, we want to be prepared not only for 3, 4, 5 different possible scenarios, but we want to get this overarching understanding of systemic indicators, so indicators that describe an energy system. And this, of course, or an energy system has more than 3, 4, 5 realistic future pathways, but indefinite number of possible realistic pathways it can take. And we want to understand what are systemic indicators that really systemically affect the feasibility of the different flexibilization or repurposing options we see. And as we are energy systems modeler, our approach is to do energy system modeling, obviously. So we, for all the 4 countries involved in our study, we prepare a simplified energy system model. But compared to other energy system modeling studies, in this case, we also focus on specific power plants that are part of the energy system. So specific CFPP sites as part of this energy systems, to bring those 2 perspectives together from the systemic energy system level, but also from a individual plant perspective, to see how at this very specific site future flexibilization or repurposing options would behave in those different energy systems. And it's not about creating one specific final result, but it's about changing input assumptions, exploring the scenario world to get this contextual understanding about factors of possible future developments of the energy system and how they would affect the operation of feasibility of the different options we see. So next slide, please. We use some in-house tools that were developed already since, I think, 15, 20 years. It's called Remix Renewable Energy Mix. This is a linear optimization modeling framework. That means it helps us to find usually cost optimal solutions to satisfy an hourly electricity demand over a year. So we have to do a lot of parameterization of the underlying model. And in the end, we can calculate cost optimal power plant setups depending on all the input assumptions that will provide enough electricity for today, but also for future scenario years. So we usually calculate starting from a base year, which is usually in the year 2020, because there we have some reliable input assumptions, but then we of course look into the future and calculate usually different scenario years in a 5 or 10 year step. In this study here, we will focus on the intermediate term, so we will calculate the base year 2020, but also future years 2030 and 2040. So this is our major tool we are using. And this tool or such a model is always only as good as the input parameters are, because based on all techno-economic assumptions of the different technologies which are part of an energy system for electricity generation, electricity storage, electricity transmission, they all affect how cost optimal future solutions for the electricity supply would look like. And by variation of those input assumptions, you will always get a different result. So this is why it's really important to have a stable and high quality input parameter basis in the beginning. So we are using renewable energy potentials and hourly time series for the possible generation of PV and wind, which are also developed in-house. But then for all the techno-economic assumptions and the base parameterizations, we try to stick to publicly available data to also increase the traceability and of the model itself. And of course, then we go into a consistency check and see if the data we could retrieve are also in line with some specific national data or specific insights we can get from national stakeholders. And we also consider or include long-term perspectives that are usually then country-specific. That means in the model we also implement, or we have the possibility to implement possible future plans for emission targets, or if there are already defined strategies for the capacity expansion of different energy generation technologies, such as gas generation or PV or wind generation or battery storages or whatever. And those are all assumptions we implement into the model, and then we use this linear optimization to get those cost optimal solutions. Next slide, please. We are using generic methods. The reason is that we are conducting 4 studies, so for 4 countries, and to keep the effort at a minimum, let's say, but also maintain the consistency between the different sub-studies, I would say, or between the different national studies. We stick to generic tools on the right, for example, just to explain what you see. This is how we come from OpenStreetMap data, in this case, for transmission lines, so a high voltage transmission grid that transfers electricity throughout different countries. In this example here for South Africa on top and Thailand at the bottom. And then we apply generic methods to retrieve this data and simplify it into simplified electricity grid, because in energy system modeling, you always have to simplify data, because if you wouldn't do that, then the computational effort would be too high, and our focus is on assessing multiple possible futures. So that's why we have to stay with a minimum or possible minimum regarding the details. And then based on those generic methods, which we are also using for all the other relevant parameters, techno-economic assumptions, installed power plant capacities, and so on. Of course, we implement then national characteristics afterwards, because they are individually then for every country we are assessing. Another important pillar of the study is the stakeholder engagement, because so we are sitting in Germany, and of course the experts of any national energy system are sitting in the corresponding countries and are dealing with the energy system. So this is why the stakeholder engagement is really important. So we can get a better understanding about really urgent questions from a national perspective, or maybe from the operator's perspective or stakeholder perspective. And we also try to get feedback on our input assumptions, because as mentioned before, a model is only as good as its inputs. So this is why it's important to at least start with high quality inputs that are close to reality. And so this is why we try to get feedback and try also to get into discussions regarding our input assumptions to see if we are on the right track. Next slide, please. And yeah, so this is already the last slide, and just giving you an outline about about what we are going to do with what I just described before. So a broad scenario assessment, what does that mean? So we are doing broad scenario variation for different possible future developments. That means, so I try to depict it on the right with this cube, but it's a bit abstract. So we have multiple possible scenario dimensions that we can describe. We can, for example, say that we expect a specific cost regression for certain technologies. Or we can say that one scenario dimensions is the development of the electricity demand over time. Another scenario dimension could be the possible expansion for renewable capacity, or many more. So there are many scenario dimensions we can define. And by combining them all, we in the end end up with a really large scenario space. That means the combination of all our input assumptions for every scenario dimension, if you multiply them all, then you get a matrix of a couple of thousand combinations that we are all calculating for every country. So this is what is meant by broad scenario analysis or broad scenario variation. So our focus is really on not providing, like Jürgen said, not providing a prediction, but covering a broad scenario space, so that in the end, the target is that the reality in the future will be somehow in this scenario space we covered. And for all those many thousands calculations per country, we always try to understand in such a possible future development of the energy system, how would be the role of one specific flexibilization or repurposing option at the site we selected for the study. So how would it behave? How would it operate in a cost optimal world in this case? How many full load hours can it achieve? What would be the required investment for the different technologies, and how is this compared to the electricity that it could provide in such a system? What is the flexibility that is required in a future energy system that takes the one direction or the other? So those are all the aspects we are interested in, and this is what we try to then describe by the so-called context factors, because any of the scenarios can somehow be characterized with some overarching indicators or context factors. We call them, for example, the penetration of renewable. It can be the degree of demand side flexibility. It can be the installed flexibility in the system. It can be what about electricity imports and how flexible are they? And also there are many, many more. So those are the context factors that can describe any scenario. And then we, for every calculation, so every scenario, we assess KPIs for our CFPP side or CFPP flexibility option. And those are then the data we compare in the end. And this is our major result, or will be our major result also from the study, the comparison of those context factors describing today's energy system and the possible future pathways it can take or developments it can take, and the KPIs of those different flexibility or repurposing options. And then by this interdependencies and this comparison, our aim is that we can get a better understanding about those overarching interdependencies and also putting words behind them. So those context factors describing different realities and then seeing that if we face a certain reality or certain scenario, then we might know which of those flexibility or repurposing options are more feasible or which are not in such a possible future. And of course, by applying the same method not only to one country but to 4 national country contexts, we try to account for even more possible realities. So yeah, I would end now, and I hope I made it a bit clearer what the systemic perspective aims at, and looking forward also for the next presentations.
Thank you very much, Andreas, for sharing shedding some light on the study that we're currently conducting. Very interesting. If there are any questions, dear participants, please feel free to drop them in the chat so we can address them later in the panel discussions regarding Andreas' presentation. Moving on swiftly, we now, as I mentioned, have a first presentation on a topic more at the on a perspective more at the operational level, and I am very pleased to welcome Dr. Claudia Weise, who is a project director of international affairs at the VGBE Power Plant Association. Dr. Weise is a process engineer and has ample experience, international experience in operational flexibilization of coal-fired power plants. And we're very happy to have her here. Over to you, Claudia. Thank you very much for joining.
Thank you, Martin, and welcome also from my side. Good morning and good afternoon. I would like to share with you some experiences VGBE gained in the flexibilization of existing coal-fired power plants. And in order to start, so next slide, please, I would like to reflect a little bit on the energy mix in Germany first, in order to show you why we had the need for flexibilization. And next slide, please. This slide shows you the electricity mix which we had in Germany last year. So you can see that the renewables accounted for almost 60% of the electricity production, and wind is our main source of energy with 28%. And the fossil fuels, our indigenous lignite, the imported hard coal and imported natural gas are still on decline. So the high share of the variable renewables, wind and PV, are a key driver for our energy system to become very flexible. So, and this might be more visible for you when reflecting a certain load profile. So next slide, please. Here you see the load profile in Germany from June this year. And you see here the contribution of the different energy sources to the electricity production. So in yellow, this is PV and the blue is wind. And one can see easily that the renewables were able to meet almost the whole electricity demand, which is displayed in pink. You also see the grayish color. So this stands for the conventional, mainly fossil-based power generation. And this is the residual load they had to provide. So residual load is the load which bridges the gap between the electricity demand and the feed-in of the renewables. Next slide, please. And this slide shows you only the contribution of the conventional part. So in brown, you see the lignite, in black, the hard coal, and in gray, the natural gas. And it's good to see that the conventional fleet has to be operated very flexibly in order to provide the according residual load. And especially the hard coal plants in Germany are flexing on a daily basis, and they are even operated in two-shifting mode, which means that they are shut down overnight or over the weekend in order to because they are simply not needed. And this brings me to the next topic of my presentation. I would like to share with you some learnings with regards to the flexibilization of coal-fired power plants. Next slide, please. Before I come to this, I would like to show you this slide, which refers to the flexibility parameters which we have in mind when we talk about flexibilization. So there are mainly 3 parameters which are very important for us. The first one is the minimum load. That is the lowest load the power plant can be operated in stable manner without any supporting fuel. Then we have the ramp rates. That is the load change in a certain time period. And the third one is the startup time and also the shutdown time of the plant. You see that I have marked here the minimum load row in this table here. The table shows you some typical figures which are achieved regarding these parameters in our plants. So you see different parameters. So the middle one is the most common one. And the minimum load is a very important parameter here for us because this is required to reduce the load of a certain power plant when the prices for electricity is very low. So in Germany, we have an open electricity market, an energy-only market. That means the power plants earn money when the demand is high, and they don't earn money when the demand is low, when the renewables are in. And during these periods, the plants need to decrease their load and as low as possible to avoid losses. And this is somehow a trade-off between shutting down the plant and taking into account a cost intense startup, or to be still in operation with a very low minimum load. So that was the key technology driver in Germany to flexibilize the plants. Next slide, please. And here I have tried to really nail down the key challenges when it comes to flexibilization. So I have structured them into 3 different dimensions. Of course, the most important one is money. So the most relevant challenge when it comes to flexibilization is how to maintain the commercial viability of the plant in the view of the reduced full load hours. So that's what flexibilization is associated with. So if you have a cycling plant, you have less full load hours and you have less electricity that is produced with the plant, and you have to have somehow a business model that recovers these loss of full load hours. So the market design is really decisive for the success of the flexibilization. And of course, you need to invest money in testing, training, and technology adaptation that might be required for flexibilization. That brings me to the to the second pillar of this, so technology. Actually, the technology aspect of flexibilization is not really a rocket science. It requires an in-depth process understanding. So you need to know what happens if you reduce the fuel to your plant, what happens to your processes there. And this knowledge needs to be reflected in the instrumentation and control system. So that's one of the key experiences which we made, that the key lever to flexibilize the plant from a technical point of view is the INC system. So the control loops should be optimized for the whole load range, and the adaptation of controls is required, and maybe also some additional automation procedures should be implemented. So this is one of the key aspects which are required in order to make the plant more flexible. Maybe there's also the requirement for some mechanical changes, for instance, to change some on-off valves into regulated valves. And last but not least, it's also associated with a modification of operational and maintenance procedures. As you can imagine, if you have a lot of startups, you have increased wear and tear of certain components, and this requires an according adaptation of the maintenance procedures. And last but not least, it's also very important to take the people on board. And this is somehow a bit underestimated in the first place. At least that reflects our experience, because the operator of the plant, they don't want to operate their plant flexibly. They are used to base load, full load operation, and they have a certain apprehension to do so. And therefore, it's really necessary to create an understanding for the necessity. Why is it important for the country that such plants are the key area to make the whole system flexibly? And so initiating according training programs and awareness campaigns are also very helpful to support the process. And we made the experience that especially simulator trainings can be of added value in this regard. Next slide, please. And we have conducted some pilot projects in various countries in India, South Africa, and Turkey under the auspices of the bilateral energy partnerships of the German government. Next slide, please. And the key focus of these projects were to do the first step in the flexibilization. And the first step is that you take a certain reference plant and do an assessment of the conditions of the plant. You assess the operating data of the past and conduct test runs in which you operate the plant at different loads and play a little bit around, so to say, and identify. Would you please go back to the previous slide? Thank you. To identify factors for low load operation and higher ramp rates. And it's also very good that you get the operators team on board, because they learn along the way and they get familiarized, and it's a very good starting point really to decrease the resistance regarding this whole topic, also from this people perspective. And moreover, the assessment of such test runs is really the basis to develop plant-specific technical flexibilization measures, and to make a plan what needs to be done in order to make this plant more flexible. Next slide, please. So this is an example. I don't want to go into detail for this slide. This is just one example from a test run evaluation for a certain type of boilers which we did in India. So we have investigated the different key areas. Here it's shown the combustion part. What could be done in these type of plants in order to really technically make this plant more flexible. So this is one of the results of these pilots which I just was talking about. So next slide, please. And this is also my last slide, which shows you the phases which we have found have to be passed in order to really make this flexible operation a routine. So the starting point is the test with the plant assessments and also the awareness raising, and they form the basis to develop a concept for a steady, flexible operation. And as I said, the INC optimization plays a key role in this regard. And yeah, I always say the higher the level of automation, the better, because then you are on the safe side and do not depend so much on the skill level of the operator's personnel. But we see in Germany that we have a very high level of automation, which really supports this type of operation. Training programs, of course, are really important, which also should be think of in the first place. And then, of course, these measures need to be implemented, and this will require a whole set of new operational schemes, including new inspection methods and life cycle monitoring procedures. Maybe it's also needed to have new staffing concepts if you come to the point that you have two shifting or whatever. And then finally, it becomes a routine. And maybe to summarize it all, so my message would be to say that flexibilization is, from our experience, not really a technology challenge. It depends more on the people who are willing to do so, who are open to new ideas. And of course, the market environment should be in favor of such a change. Otherwise, it won't happen. And yeah, so I'm at the end of my presentation, and I'm thankful for your attention.
Thank you very much, Claudia, for this excellent presentation. Again, a reminder for me to please share your questions in the chat or via the Q&A function. I'm certain we will have the time to dive a bit deeper into some aspects of Claudia's presentation. But for now, we will move over to we've heard a little bit about experience in South Africa and India, and now we will look at the country case of Chile. So we're very happy to have today with us Jorge Moreno and Victoria Fröhlich from energy consultancy Inodú. Jorge Moreno is a senior consultant at Inodú and has over 20 years experience in the energy sector. Victoria Fröhlich is a civil engineer specializing in environmental engineering, also working at Inodú. I will, without further ado, now pass the floor to Jorge and Victoria. And yeah, thank you very much for joining us this early in the morning in Chile. Thank you.
Yeah, hello, Martin. Thank you for the introduction. And we're going to be talking about our experience in flexibilization, some of the coal-fired power plants that we have in Chile. If we can go to the next slide, please. Thank you. So in this slide, we present just a little background about the energy system that we have in Chile. And you can see in this graph the yearly generation by source that we have in the country. And you can see also that we face 3 energy transitions. And the second one, which is around 2005 to 2006, was triggered by a reduction in imports of Argentinian gas. So we faced a severe energy crisis that year that actually triggered the construction of some new coal power plants, as you can see in the black color there. Coal energy started to increase after that energy crisis. And that's why in Chile we have fairly new coal power plants today because of that crisis. And then the third energy transition started maybe in 2008 to 2015. We see the installation of renewables. We see the installation of solar in the orange color and wind in green color. That was really rapid in the last maybe 10 years. If we can go to the next slide, we can. Perfect. So I'm gonna dive in the third energy transition that was triggered by the rapid installation of solar and wind, and maybe in the last 12 months we can also start to see installation of batteries in the red color in the graph on the left side of the slide. We can see how rapidly the solar and wind capacity growth in Chile between 2017 and today, basically. And this rapid installation mainly enabled the retirement of some of the coal power plants that we have in Chile. We have retired 30% of our coal capacity. And in the right side of the slide, we can see a graph that shows the age of the coal power plants and the gas power plants that we have in Chile. And as we can see in the pink color, those are the plants that we have already retired. So we start to retire the older plants because they are easy to retire. But the new plants that we still have in operation in the black color, those are plants that are relatively new, so they are less than 20 years old. So those plants are not going to be as easy to retire. And it's also important to mention that the gas power plants that we have in the gray color, you can see that, those plants are older than the coal power plants because those coal power plants were installed after the gas crisis that we have. So to close those new coal power plants and rely on those older gas assets would pose a risk to the system. And that's why those coal power plants cannot be retired yet. But the thing is that the energy transition was triggered by the rapid installation of renewables, but also because of the flexibilization of the coal power plants that remain in operation. And we will see more about that in the next slide, please. Perfect. Here in this slide, we can see the operation of the Chilean system between 2017 and today. We can see the average hourly generation for the average day each year. And as you can see in the left side of the graph, solar, which is the orange color, started to integrate really rapidly in the system. Also, wind started to integrate, and that caused a decline in thermal generation. You can see that coal, which is at the bottom part of the graph, started to decrease in the last 10 years. But it remained important today. We can see that we still have coal generation today, and that is because coal is needed when the sun is not there, for example, during the night, and also when there are days without as much wind, or for example, in days or in the dry season that we have in Chile. So in dry season, hydro generation really decreases, and we need to rely more on coal and gas. But as you can see in the operation of coal has shifted their operational mode to allow more renewables, especially sun. If you see the coal operation in the first part of the graph, so in 2017, you can see coal operating really in base load without changing their output during the day. But as you go through the years, you can see that coal started to become more flexible. Coal started to decrease their generation during the day to allow more renewable, especially solar, and to increase their operation during the night to basically be able to supply the demand that we have at night. And it is really important, this flexibilization of coal power plants, because as those coal power plants remain in operation during the day, but at a really low output, they can still provide essential service to the grid that they provide, such as inertia, voltage control, frequency control, which are not yet renewables are not yet fully able to provide. So to have those coal power plants in operation during the day at a minimum load, it's really good for the system. It allows more integration of renewable, it allows the decrease in thermal generation, and it allows to maintain the security of the grid. And in 2025, you can see the emerging role of batteries. We have some batteries, you can see that in the red color. They charge during the day and they start to discharge during the night, and they will start to displace some of the thermal generation, but we are not there yet, so we still need some coal and gas generation. If we go to the next slide, we can see how we have been able to reduce the minimum load and flexibilize those coal units. In this slide, we present two graphs that compares the minimum load of coal power plants in Chile and the US in 2017 and in 2025 today. I'm not going to go into details about what the minimum load is because Dr. Claudia presented it very well. So I'm just going to say that in 2017, coal power plants in Chile, we can see that in the red color, were not as flexible. They were inflexible. In this graph, we can see each circle is a coal power plant, and that is the cumulative distribution of all of the coal power plants in the US and in Chile in order from more flexible to less flexible. So the units in the left side of the graph are really flexible or have a really low minimum load, and the units at the right part of the graph are more inflexible and have a higher minimum load. And the minimum load here is presented as a percentage of the nominal capacity of each unit. And we can see that in 2017, all of the units in Chile have a minimum load between 31 and 66%, which is not really flexible. But from 2017 to 2025, we see a big reduction in the minimum load of all of the units in Chile that are in the red colors. And right now, our units are operating really flexible with a minimum load between 20 and 40%. And actually, the units that are less flexible, maybe around the 40%, are in the blue color. And those units are expected to retire or reconvert really soon. So they are not really working and reduce their minimum load because they are not going to be operating in the next maybe 2 years. And right now, 9 of the units we have in Chile are operating at a minimum level load of between 20 and 25%, which is really, really low. And 2 units, which are maybe the more orange colors, are currently working or reduce their minimum load from 30, maybe 31 to around 20 and 25%. So units in Chile are actually outperforming a lot of units that in the US and actually some units in Australia as well. And Jorge will right now tell you how we managed to do that.
Yeah, so next slide. So first, important to emphasize that the Chilean power system is an isolated system. So all the flexibility must be provided by units, okay, within the system. So okay, so in this case, okay, we assess the impact of further reducing the minimum load of coal and gas units on the system operation by year 2027. Okay, in 3 different scenarios. So business as usual, intermediate, and aggressive. Okay, the scenarios, okay, so consider different minimum load levels. Okay, so the business as usual is kind of the average minimum load that we can find today in the system. Intermediate level is a reduction to 24%, and the aggressive is a reduction to 17%. Okay, and for coal units, those levels implies the operation with 1 mill. Okay, and with gas units, okay, so the aggressive scenario implies a regulatory change in limits for NOx emissions. To do that assessment, okay, we use Plexos to model our power system. We have a complete representation of the power system with transmission constraints, security constraints, different scenarios for hourly variation of renewables, and so on. The model is on an hourly basis to have a complete and detailed assessment of the power system. And here at the system level, okay, we assess different metrics. For example, curtailments for renewable energy, out of merit dispatch, CO2 and other emissions, cost of operation, reliability, and adequacy of the system. And the same analysis, so this is important, so the same analysis can be done at the independent power producer level. In this case, it's important to assess that an increased flexibility will have an impact on load following operation, to chief operation, extended outage operation, competitiveness, and profit and loss. By doing so, we can increase the visibility, okay, of not only as system-wide benefits, but also the benefit at the independent power producer level. Chile's thermal power plants already are, as Victoria mentioned, among the most flexible globally, but a further reduction of minimum load, though marginal, can still deliver some value, okay, in different system-wide metrics. So in the next slide, we show the benefits that we estimated, okay, under the aggressive scenario, okay, and you can see that we have improvement, in this case, reduction of thermal generation and out of merit dispatch. This is very important for the cost of operation of the system. Also, we reduce curtailment. We assess also a reduce of system cost and the marginal cost as well, emissions and pollutants. Okay. So in next slide. So as we assess, okay, the impact as at the system level, now we will show a case in that present how we have implemented, okay, those measures at a plant level. Okay, so in this case, we present a practical application just to show how to achieve what we are suggesting. So we started this process in 2022. okay, where our team supported Wacolda with the application of the every high-level flexibility assessment to review 10 areas related to the flexible operation of their units. And just to give a brief context, Wacolda is located in the north of Chile. They have 5 coal fire units. Each of them is approximately 550 megawatts. The benefits of improving the flexibility of the units were evaluated by modeling the dispatch of the power system under different scenarios, the same thing that we showed before. Okay, for that process, we also use Plexos with a complete representation of the power system. Okay, in this case, we will skip that part. Finally, so minimum load reduction trials were conducted to improve the flexibility of the units. Coal-fired power plants typically operate with 2 or more mills. A single mill operation is not a standard practice. However, with the growing integration of renewables in Chile, operators have recognized the need to apply process innovation in a reliable and controlled manner. In order to do that, as other speakers have mentioned, we did a systemic approach to act on people, processes, and technology in order to align flexible operation objectives with maintenance practices and to mitigate failure modes. So the next slide. Okay, so the team evaluated the flexibility of the units across 10 different dimensions. Okay, so as I mentioned, we use the flexible, so the EPRI tool to assess the impact of flexibility in equipment operation mode, pressure part management, operations, maintenance, combustion and performance, instrumentation, control and automation, environmental control, cycle chemistry, turbine and generators, and balance of plant. The initial flexibility assessment showed good performance, but identified some vulnerabilities. With that, the team defined a clear roadmap with minimum load reduction of the Wacolda's units. So next slide. Then in another stage, okay, next slide. No, previous one, this one. Okay, so then in this one. Okay. In another stage, the team validated the reliable and stable operation at the new minimum load target through testing. Here it's important to emphasize that we conducted tests with only 1 mill operation. Something that is very important is to plan for the switch from 2 mills to 1 mill operation at minimum load and build confidence in the operators in that process. The team assessed operational risk, for example, in the operation of the feed water system, at temperatures, SCR, and other subsystem of the power plant. We observed a more stable operation, actually, and an improved combustion performance compared to 2 mill operation at the low load. Next slide. So finally, with the conclusion, so the energy transition process requires a reliable operation of thermoelectric facilities that remain in operation. This is something that is applicable in every country. And the reliable flexibilization of thermoelectric facilities is driven by operators supported by strong leadership commitment of the plant level and requires a systemic approach. So the flexibilization of thermoelectric facilities should be viewed not as a replacement for long-term coal phase-out, but as a best practice to support a smooth transition. It enables thermal units to operate at a lower loads while remaining online and ready to support the variation of renewable resources. So it provides additional time also for the system to adapt in a more coordinated manner. Flexibilization also is a very cost-effective and impactful measure that leverage the capabilities of existing operational assets. Chile experience show that the technical barriers to flexibility can be overcome with target assessment, operators engagement, and practical testing. And I think that is very impressive because in our country, of the 12 coal-fired facilities that will remain operational by the end of next year, 9 have a minimum load below 25%. I would say that this is state of the art, and 2 are currently in the process of reaching that target. Thank you.
Great. Thank you very much, Victoria and Jorge. That was very interesting on the case of Chile. Please, dear participants, you can check out the full case study on impact of thermal flexibility and operational performance in Chile power system in the chat. There's a link in the chat, and you'll find it on our Knowledge Hub. So we're now left with some roughly 20 minutes for our discussion. Dear colleagues, dear participants, please feel free to share your questions in the chat and in the Q&A function. I've already seen that there has been one question asked on the first presentation, but that has also been addressed via the chat. The question was from Abrahama Akhtam Halim on the representation of flexibility properties in coal-fired power plants. I think we can skip that question and start maybe with some more broader guiding question to kickstart the discussion here. Of course, as a just energy transition and as a coal phase out project, one question that looms large regarding the flexibilization of coal-fired power plant is, does it actually support a coal phase out? And what about the actual emission reduction? So I wanted to ask and use this opportunity to ask our knowledgeable panel. Maybe we can start at this level with Claudia. If you have any knowledge on the effect on flexibilization of coal-fired power plants on emission reductions, and maybe if there's also a perspective on the short term or the longer term, if that's fine for you.
Thank you, Martin, for this question. Actually, I don't have figures with me, but maybe to have a general answer. So as I already mentioned in my presentation, flexibilization goes along with a reduced number of full load hours. So that means that you produce less electricity with your certain power plant, and this gap between full load and the reduced load which you have is supplied by renewables. And this reduction per se is the consequence of higher share of renewables. At least that was the situation in Germany. So that it's a trade-off between the reduced hours of the power plant, less CO2 emissions and other emissions, and more renewables, which finally results in less CO2 and other emissions. So that's the fact in Germany. So we have reduced our emissions related to electricity production to a large extent, and I think we are in line with our climate targets in this regard. But in other countries, the situation might be different because you have still a increasing demand of electricity, and you need to build up capacity. And so you increase the share of renewables, but you also increase the number of maybe fossil plants. And so you cannot really identify the extent to which the fossil fuel-based power plant full load hours reduction accounts for emission reduction. I'm not sure whether this was clear to be understood. So I think one needs to differentiate between countries with no growing electricity demands, so where the renewables really push out the fossil fuel out of the market. So then you have a clear decline of emissions. but in markets with an increasing electricity demand, you open the door for the increase of renewables, but you might be not able to measure it immediately because you also have an increase of other energy sources because you need to match the demand somehow. So, but finally, there is no other way around to make the plants flexible and to reduce the full load hours. So I think it's a no regret strategy to do so. So emissions will be reduced immediately or maybe in the longer run.
Great, thank you. Thank you very much, Claudia, for this very comprehensive
Sorry.
reply. Also, colleagues from DLR and Inodú chip in if you would like to add something to that question. That is of course quite important to get an understanding of where does this topic situate regarding emissions reductions. And I see also a lot of questions in the chat by now, but I would like to give Andreas also the chance to reply.
Yeah, thank you. Yeah, I just also can say that I support what Ms. Weise just said. I think from systemic perspective, again, it's always about the need for flexibility and how do I supply it. So the need for flexibility evolves with increasing share of renewable capacity. So if there's not a lot of renewable capacity installed in the system, I don't need a lot of flexibility because the fluctuating energy does not really affect my system if there's not much fluctuating capacity installed. But of course, with increasing fluctuating capacity, which is usually solar and wind, there is an increase in the necessity of providing flexibility. And this flexibility can be supplied by different sources. One can be increasing or decreasing the minimum stable load. Another one can be the additional installation of other storage types, for example, battery storages, or you have pumped hydro or whatever. So there are different available technologies that are capable of providing flexibility. But in the end, I think it's the mixture and definitely also the national context that decides which is the best way to go. So do you have, for example, a gas infrastructure in your country or not? In the German case, for example, a way of providing flexibility currently is the increase in gas capacity again, but just because there's already an existing gas infrastructure. So it's a lot of, again, context factors also that are affecting possible the feasibility of different flexibility options. But of course, reducing the minimum stable load for existing power plant fleet provides more flexibility. So yeah, but depending on the context.
Thanks, Andreas, for the reminder also to look at flexibility at systems level and look at the operational flexibility of coal-fired power plants as one option to increase flexibility within the power system. So let me ask Victoria and Jorge two questions very interesting here in the chat on what about the impact on power prices. So what is the effect on flexibilization on power prices, specifically in the case of Chile? And we'll take a second question as well. Could you, Victoria and Jorge, could you please clarify what the system redundancy requirements, how they were met, and yeah, to just elaborate a little bit more on these technical aspects.
Okay, well, thank you. So so let's start with the second one, because the second question will help us to understand the first one. So where you are integrating when you integrate in a power system more renewables, particularly inverter-based resources, so you really need to have a very clear assessment of your transmission constraints. Okay, and in order to do that, you need hopefully a complete representation of the power system, of the transmission system, because if you don't represent the transmission system as a whole, at the end you will miss a little bit the need for flexibility, because renewables start integrating, okay, in some areas in the system, and that will require in some particular areas even more flexibility from the assets that you have installed, okay? And in our context, for example, in Chile, we have the Atacama Desert in the north, okay, with a lot of IBRs, okay, inverted pressure sources. So you need, okay, so from the point of view of system redundancy, okay, you need to comply with some security constraints. And security constraints are not only related with transmission constraints, are also related with voltage control, inertia, primary frequency control. Okay, so what we have in our system, and you probably may face the same challenges in other systems, is that you need somehow mass run operation of some thermoelectric facilities just to provide to the system the security, okay, services that the system needs in order to operate in a reliable manner. Okay, so in our power system, we have the N-1 requirement, but also, as in other power systems, you have voltage control requirement, primary frequency control requirements, voltage control requirements. So before you install other systems like synchronous condensers that will take time, okay, or grid forming inverters that also will take time to certify, okay, you need those services from coal facilities. And to provide those services, even though you have a lot of renewables, okay, so if you have high minimum load, at the end, this will increase curtailment. And as the marginal prices at those hours will be very, very low, probably will not be enough to cover the variable cost of operation of the thermoelectric facilities. So you will need, from the regulatory point of view, uplift payment. Okay, so to pay to the thermoelectric facilities for the not covered cost, okay, when they run at the minimum load. So if you reduce the minimum load, okay, so you will have the side benefit of reducing also the uplift payment of the system. Okay, so that's one benefit. Okay, and we show that metric in the report that we published. Okay, and also, okay, if you have on the other side, if you have like the coal facilities operating at a very low load during the day, then when you need to wrap up at the end of the day, okay, so you will have a more smooth transition. So probably the marginal cost, as we also show in the simulation, okay, will be lower, okay, at night as well. Okay, so you have two benefits. Okay, so the benefit of reducing uplift payments and also the benefit of reducing a little bit the marginal cost at night.
Yeah, if you don't have the coal power plants in operation during the day, then you cannot use those coal power plants during the night. And then you must rely on other peaking stations, maybe diesel peaking stations that are more expensive. So that's why the marginal cost at night gets also reduced by reducing the minimum load of the coal power plants.
Great, thank you very much, Jorge and Victoria, for explanations. Of course, in a specific country case of Chile with a liberalized electricity system, I should put forward as context. And Jürgen also wanted to reply, if I got that correctly.
Yeah, thank you, Martin. First of all, thank you very much for the excellent contributions of Claudia Weise and the team from Chile. I completely agree to your point of view. And from the systems analysis perspective and over 35 years of experience in renewable energy integration, what we said in the beginning, I can give you a clear answer to your question. The clear answer is it depends. So every energy system is different. And you always have to take a full comprehensive system approach, looking at all the context factor and key indicators. For example, the main goal is always security of demand. And then you have to look at the possible RE expansion rates, possible storage options, high voltage transmissions, policy boundaries, and investment possibilities. So you cannot just take one power plant just out of the energy system. You also have to look how will the energy system develop in a country in the next couple of years up to 20, 30 years, because typically power plants have been operated over 20, 30, and even longer. As we see in countries like South Africa, they will operate their coal power plants 50 years or more. So it depends. Every country is different, and you always have to look at a full comprehensive energy system to identify clues and answer for the solution of tomorrow.
Great. Thank you very much for this addition, Jürgen. There's more questions. Again, thank you, participants, for joining a lively discussion. We won't be able to tackle all questions, but I wanted to give a chance to address maybe one last round before we wrap up. There are, let me just retrieve here now from the Q&A section. So one question was, it would be great to better understand how we can assess when the flexibilization of coal-fired power plant makes sense and is necessary for the system in a transition to renewables. For example, how many flexible coal plants do we really need? Also, when is coal best suited to provide flexibilization in comparison to other fuels, for instance, gas? Thankful for, so we can also suggest some literature in that regard. That's an open question again. Who would like to tackle that one? Andreas, please go ahead. First come, first serve.
Yeah, I fully agree to this question, and I think our target is that we can provide some answers with the study we are currently developing, because of course you always have different options in the system, and you have different. You always can also go more into detail, because that's also part of the response I gave to the other question in the Q&A. Usually, at least for the study we are doing, I don't know how the team from Inodú did their studies, but we are working with hourly resolution, for example, and hourly resolution might be enough to get insights on minimum stable load. But might not be enough to get insights on the ramping rates, which are usually important to ramp in between just a couple of minutes, for example. So you can always go further and further, also in the level of detail, but part or overarching question of our study is especially targeting also in the question you just put there. So to see what options do we see in the system, and then from a cost perspective in this case, also considering a possible CO2 emission costs, of course, to see what are at least cost optimal ways of providing flexibility that can be provided by all means of technologies.
Yeah, just to complement that. Okay, so from the Inodú side, so we also use an hourly assessment, okay, with a complete representation of the transmission system and all the variation of renewables throughout the year. Yeah, and this is very context dependent. So we have done this analysis also in this type of analysis in Dominican Republic, Peru, California. And regarding one of the questions, okay, so it's very important also to understand the adequacy objectives of the system. Okay, so how much reserve margin do you want in the system? Okay, how will you complement other resources, and how many units you will maintain online? Okay, not only with this type of analysis like Plexus or other tools, but also doing so kind of detailed system analysis with Chilean or other tools to analyze, okay, so the frequency control requirements, voltage control requirements. I would say that probably the need for the complement of thermoelectric facilities will come not only from the flexibility side, but also for requirements such as voltage control and primary frequency control in the system. Okay.
Great. And with that, there's I mean, there's a couple of points here that we won't have time for addressing in full, but I would like to look at one question in particular here that I think could be of interest also for a lot of colleagues and participants. There's a question on commercial case studies. I think, Jorge, you alluded to some examples that you might have found in your work as well, but maybe I would like to address this one to Claudia, if I may. Do you have any commercial case studies showing the impact on the financial position of coal-fired power plant asset owners? And then follow-up questions, are there approaches to use carbon credits to compensate for any earlier retirement or the reduced number of full load hours? If you have any hints on that question, would be great. Otherwise, I can also elaborate a bit on our partner organizations working more specifically on the financing aspect of the topic of today.
Actually, we at VGBE, we have not done commercial investigations. So I can just say in Germany, the plants were required to do so. Otherwise, they would be out of the market. So it was a question of survival for our plants. But I know in other countries, and I think a lot of questions relate to this, if you have a regulated market, what are the costs and how can be somehow a compensation mechanism installed? I know that in India, there have been a lot of studies how to manage this on a system level. And I think they are also published. So I would share these study links with you, Martin, and maybe you can share this with the questionnaires or with the audience. So that's what I could contribute at the moment.
Great. Thank you very much, Claudia. And with that, we're wrapping up. Again, if you're more interested in the financing aspects of this question, we also work together with partners from the Powering Past Coal Alliance and also have exchanges with the Rocky Mountains Institute that tackle these questions regarding policy schemes, financing for flexibilization and repurposing options more in detail. Thank you very much for your attention today, dear participants. Before you leave, I would like to remind you that we would really love to hear your feedback on today's expert exchange. I gained a lot of insights and would like to really thank our distinguished panelists. So please, if you could just scan the QR code in the presentation right now. And take 2 minutes to briefly just assess the expert exchange of today. We are also happy to share more news on upcoming expert exchanges and other events that the IKI JET project is hosting via our newsletter. You can sign up via our newsletter and subscribe to it via the link that is now visible on the slide. So it's on the Knowledge Hub, jetknowledge.org. And if you have any questions regarding the presentations of today or any more detailed questions on specific part aspects, please feel free to reach out to us. You see our contacts in the slide today. And with that, I wish you a great rest of the day and say goodbye. Thank you very much for your attention.
Goodbye.
Bye. Thank you very much.
Thank you. Goodbye.